In my last video, we discussed the concept of entropy from a purely mathematical perspective. Today, I want to link the concept of entropy to two of its other definitions and show how it applies to physical systems. Let's begin with a quick recap. We started with a box of gas molecules, and we stated that this system had a certain energy, volume, and number of particles, and then we introduced the idea of a microstate. A microstate is an arrangement of all of those particles in a box that satisfies the conditions of the system, and we said that each microstate has an equal probability of occurring. To simplify the math, but to keep the concepts the same, we then transitioned to talking about flipping coins, and we saw that as the number of times that we flipped a coin increased, the probability that getting a highly ordered configuration of coin flips becomes very small, and we were likely to see a disordered arrangement of coin flips simply because there are so many more ways that can happen. Returning to our box of particles, we then translated this to conclude that with a very large number of particles, our box is going to appear to be highly disordered, and our system will tend towards states that appear less ordered. Thus, the number of ways that a system can be arranged can be taken as a proxy for how disordered the system will be. Finally, we derived the Boltzmann entropy equation, where entropy, S, is equal to Kb, Boltzmann's constant, multiplied by the natural log of omega, where omega is the number of microstates. That last bit of the video was pretty technical, and unfortunately the derivations that we're going to be going through today are even a little bit more technical. Because of that, I'm going to give the conclusions of this video here with the equations, and if you want to skip the derivations and move on to more practical applications of entropy, that's fine. The first equation that we're going to derive is going to be the Gibbs entropy equation. The Gibbs entropy equation states that the entropy of a system is going to be equal to minus the Boltzmann's constant multiplied by a sum over all the possible states, where we take the probability of a given state, we multiply it by the natural log of that probability, and then sum all of those together. The next equation that we're going to derive is going to be an expression for temperature. And we state that the temperature of a system is going to be equal to how the energy of the system changes with a change in entropy. The final equation that we're going to derive is that the change in entropy of a system is going to be equal to the heat divided by the temperature at which that change occurs. This video is going to go over the derivations of all of these equations, and we'll be using them in practical applications later. Let's first start by returning to the Boltzmann entropy equation and its mathematical form. Let's talk a little bit more about why we took the natural log of the number of microstates. We dealt with microstates a lot in the last video, and at the end we said that there was a problem with working with microstates. The problem with working with microstates is that if we double the size of our system, the number of microstates does not double. Instead, we show that it becomes squared. We wanted a value that relates to the number of microstates, but it is additive, such that if we double the size of the system, that value becomes doubled. And we showed that the easiest way to do that was by taking the natural log of the number of microstates, and then everything would work out the way that we wanted it to. We then threw in this extra constant, this Boltzmann's constant, to kind of give us units for this new value, and we left it there as a mathematical convenience. However, that definition of entropy is not just a mathematical convenience, and we're going to show how this entropy is actually a real value that has a real physical meaning. First, before we jump into that, let's derive the Gibbs entropy equation, another common equation that people use to describe entropy, and just like the Boltzmann entropy equation, this equation is often thrust onto students with no explanation. We determined in our last video that each microstate was equally likely, and we stated that each microstate had a fixed energy, volume, and number of particles. We're going to introduce another term here, which is known as an ensemble. And for example, when we have all the states that could have the same energy, volume, and number of particles, we're going to call that the microcanonical ensemble. However, there's lots of other ensembles that we're going to be working with over the next several videos. We're going to introduce a new ensemble, which is known as the canonical ensemble. In this ensemble, just like how we had omega number of microstates in the microcanonical ensemble, we're going to say that we have M systems, and each of these systems have the same number of particles and the same volume. However, we're going to say that all of our M systems are in contact with each other and they can exchange energy. Because they can exchange energy with each other, That means that not all of these systems are going to have the exact same energy. However, due to conservation of energy, if we have all of our M systems together, then the total energy of all of our M systems is going to be fixed, but one of our systems may have a little bit more energy than another. There is something else that's fixed here in this system, and we're going to jump into that later in the video, but I'm not going to tell you what it is right now. Earlier, we considered the number of ways that we could distribute a fixed amount of energy to these individual particles in the microcanonical ensemble. Now, let's consider the number of ways that I can distribute energy to all of these systems. For example, of all of our M systems, I could take all of the energy of the system and I could give it to one single system, and all the rest of the systems would have zero energy. That could be one way that I could distribute this total energy. Or I could distribute the energy more evenly, or I could give some more, some less. There's lots of different ways that I could distribute this energy. Now, if one of our M systems had all of the energy, and all of the other systems had zero energy, that would be a very ordered state. So what we're going to be doing is we're going to be asking about the entropy of all M of our systems. We want to ask ourselves, what is the number of ways that this ensemble of systems can be arranged? And then we're going to get the entropy of this collection of systems. Okay, time out. Let's take a break for a minute. Honestly, this seems very bizarre, asking about the entropy of an ensemble of systems that are all in contact with each other and can exchange energy. In our last video, we were talking about the entropy of a collection of gas particles, but this seems to go a step too far. In reality, this is going to be an exercise in some very unusual mental gymnastics, but in the end, it's going to help us determine an equation that works. I promise. To start, we're going to return to the permutation formula. Except in this case, instead of having just heads or tails, which is the only option, what we're going to have here is the amount of energy that's given to a certain system. So instead of just having two parts in the denominator here for the permutation formula, we're going to have lots of different ones where each individual factorial represents a certain number of ensembles that have a given energy. Now, using this permutation formula, we get the number of ways that these things can be ordered, and we can plug this now into our Boltzmann entropy equation, and we get that the entropy is equal to the Boltzmann constant multiplied by the natural log of this permutation formula. We distribute the natural log, and then we're going to use the properties of logarithms to turn the second term into a sum. This looks pretty messy at this point, but we're going to fix this by using something known as Stirling's approximation to help us solve it. Taking the natural log of a factorial like we have here in our equation seems like it would be really painful, and the truth of it is that this is. If you were to actually do this rigorously, this would be a very difficult computation to do. However, there's a relatively simple approximation that we can use, and it's going to simplify things a lot for us. The natural log of some x factorial is approximately equal to x multiplied by the natural log of x minus x. This is known as Stirling's approximation, and this formula only works for very large values of x. If you had like 10, for example, and you did natural log of the factorial of 10, and then you did the Stirling's approximation, it's going to be off by a bit. However, if you're moving to very large numbers of particles, like let's say a mole of particles, 6 times 10 to the 23, then the Stirling's approximation is going to be very, very close to being correct. So we're going to go ahead and we're going to use this approximation here. Using this approximation, we go ahead and we rewrite our formula, and we will distribute the summation. Next, if I was to sum up all mi states, this would be equal to m, so then we can see that we're going to get some nice cancellation here. Next, let's move our formula to be using probabilities instead of mi. Of all of our systems m, the probability of selecting a system with an energy corresponding to mi would be mi divided by m. Rearranging this formula, we get that mi is going to be equal to m multiplied by pi. Substituting this in and doing some simplification with natural log rules, moving our summation around, and then moving out some of the terms of the sum, we see that we have a sum over all the probabilities of our states, which simplifies to 1, and we get some more cancellation. At this point, we get that the entropy of all of these systems is the negative of the Boltzmann constant multiplied by m, multiplied by the sum of the probability of a state, multiplied by the natural log of the probability of that state, over all states. Finally, if we want to find the entropy of just a single system with n number of particles in volume V, all we have to do is divide by m, and that's going to give us the average entropy of the system. Thus, we have now derived the Gibbs entropy equation, which is very useful if you know how many states are probable and their probabilities. So now we've got two different expressions for entropy, and they're actually equivalent, and which one you're going to want to use is going to be based on the information that you have. So one last check of this is that we're going to substitute a system of equal probabilities like we had in the microcanonical ensemble and see if we can recover the Boltzmann entropy equation. We're going to go ahead and we're going to do some simple math right here, and we see that we can, and then we can determine that the Boltzmann entropy equation is actually a simple case of the more general Gibbs entropy equation. Now, at this point, I want to give a word of caution. When we derived the Boltzmann entropy equation, it was exact. We determined that entropy was a descriptor of a system, and we defined it to be the natural log of the number of microstates that a system can have multiplied by some constant number. The Gibbs entropy equation is not exact in the very sense that we made an approximation. Before we used Stirling's approximation and we had those factorials in there, it was exact. However, as soon as we made that approximation, it became an inexact relationship. At the end of the day, we mostly will never have to worry about this, considering that the systems that we typically look at are very, very, very large collections of particles, and Stirling's approximation is quite excellent. But it is useful to keep in mind that we made this approximation under the very small possibility that you're working with the entropy of very small systems, and in which case this formula is going to be less than precise. However, if you're working with very, very small systems, then you could go back to using the expression with the factorials and you would be just fine. All right. Hope everybody's still with me because that was quite a bit of derivation and we still got more to do. At this point, we have two expressions for entropy. There are at least two more that we will want to eventually derive, one of which we will do today. But at this point, you are quite well set up for solving many theoretical problems regarding entropy. And we have somewhat of an idea of what entropy is and why the universe tends towards disorder. It's simply a probability argument. Recall our coin flips from the last video. As systems get larger and larger, the probability of a system ending up in a highly ordered state becomes minuscule, and systems will evolve if given the chance to states that are much less ordered than the ones they started in, because there are so many more disordered, in quotation marks, states. This is only a feature of statistics. There are no grand underlying principles as to why systems tend to disorder other than it being a statistical process. All right. So for today, we have one more step that we want to take regarding entropy, and this is the definition for classical thermodynamics. Everything that we've been doing up to this point has revolved around statistical thermodynamics, and it is based on the theory of atoms and molecules. However, thermodynamics has been around for a lot longer than the atomic theories, and entropy has been used for much longer and in a different way than we've presented it so far. It was actually used empirically when thinking about heat engines, and although nobody really understood it at the level that we now understand it, we're going to drop the original definition that they used here. A change in entropy of a system is equal to the heat of that transformation divided by the temperature at which that change happens. For example, you can measure the entropy change in a pot of boiling water to steam by measuring how much heat you have to put into the water to turn it into steam and dividing it by the boiling point of water in Kelvin. Let's show how we can derive this experimentally determined equation for what we know about entropy already. And once again, I'm going to warn you that this is going to be pretty mathematically intense, and I'm trying to make it as simple as possible so that you can follow it. Suppose that we have a system, and we can divide the system into two parts, A and B. The total energy of the system will remain the same, and each part of the system has its own energy and its own entropy. However, energy can flow between the two systems. The total energy of the system must be conserved, however. At equilibrium, the entropy of the total system will be maximized due to the statistical nature of entropy, and the entropy of the total system is equal to the entropy of system A plus the entropy of system B, as we covered in the last video. Let us now consider a graph with the energy in system A on the x-axis and the total entropy on the y-axis. As I mentioned, the total entropy will be maximized, and so it may look something like this. And where this maximum is, that will be the energy of system A. If we were to increase or decrease the energy in system A, it would decrease the entropy. Or in other words, the derivative of the total entropy with respect to the energy in system A is equal to 0. Now we're going to go ahead and rewrite this equation. The total entropy is equal to this entropy of system A plus the entropy of system B. So we go ahead and we expand this equation, and now, due to the conservation of energy, any change in the energy of system A is equal to the negative change in the energy of system B. So we go ahead and substitute this in, and we're going to move things to this side, and we can see a final relationship. The derivative of the entropy with respect to energy must be equal between two systems that can exchange energy with each other at equilibrium. Some of you can probably jump to the conclusion of this, but I think one more illustration will really help nail this down. Suppose that we take a cold piece of metal and a hot piece of metal and lay one on top of each other. The pieces of metal are isolated from everything else. What's going to happen over time? The cold piece of metal will heat up, and the hot piece of metal will cool down until they've reached the same temperature. What drives this process? I think that we can safely assume that it is driven by entropy, as the new system that we've created from these two systems is going to try to maximize the entropy. These two pieces of metal are in contact with each other. They can exchange energy with each other, and at equilibrium, they're going to have the same value of temperature. This seems very familiar with the quantity that we described above, and you can probably guess that it is related. We will define this relationship that two objects that are in thermal equilibrium have with each other as the inverse of temperature. This is a very strange definition of temperature, but it's really what you might say the most fundamental definition of temperature. We can now go ahead and rearrange this equation to state that the change in entropy is going to be equal to a change in energy divided by the temperature. And as this process is a heat-based change in energy, we just put two pieces of metal together, for example, we will rewrite the change in energy as being heat, and now we have derived the empirical definition of entropy. As a final side note, recall when we were talking about the canonical ensemble and I said there was one other thing besides the number of particles and volume of each system that was fixed. Because all of those M systems are in contact with each other, the last thing that is fixed is going to be the temperature. And that's because all of our systems could exchange energy with each other and they were at thermal equilibrium. Let's do two things to just double check our conclusion and show that the entropy is what we really want to be working with, not the number of ways that a system can be arranged. Suppose once again that we have two systems, A and B, but they have different temperatures. We place them together, and we want to know about how the entropy changes. Once again, we know the total entropy change will be equal to the entropy change of system A plus the entropy change of system B. And using this expression, we can rearrange this to read that a change in entropy is equal to a change in energy divided by temperature. Finally, due to conservation of energy, such that the change in the energy of system A is equal to the negative change in the energy of system B, we can rewrite our expression in terms of the energy of system A and the temperature. Finally, we see that for this expression to yield a positive result, as the total change in entropy for the system must be greater than or equal to 0, If the temperature of system A is smaller than the temperature of system B, then system A needs to gain energy and system B must lose energy, and thus system A, which was colder, got warmer, and system B, which was warmer, got cooler. Lastly, let's show that entropy is far superior to the number of ways that a system can be arranged when dealing with real systems, and to do this, we will try to derive temperature like we did above, but only using microstates. If you recall from the last video, the reason that we define entropy as a logarithm of the number of ways that the system can be arranged is because we wanted entropy to be additive, as we've used multiple times already. If instead we use the number of ways, where the total number of ways the system can be arranged is omega A multiplied by omega B, and we use the same substitutions, we see that we get something much nastier than when we got using entropy. And there isn't an easy relationship to pull out where the change in the number of ways that a system can be arranged with the change in energy could be easily related to temperature. Thus, although I stated previously that entropy was just a mathematical convenience for us, because it was, at this point we can now see that entropy really is a real quantity describing systems, as much as temperature or energy is. Thank you for watching this video detailing entropy more and bringing it into the experimental realm. If you enjoyed this video, please like and share this video as it helps considerably in increasing outreach. If you want to see more videos on chemistry and physics topics, please consider subscribing to the channel. I've linked my Patreon page in the description below, and if you would like to support educational content like this, please consider donating. Finally, please comment down below if there's something you feel like I could make more clear, or if there are other topics that you would like me to cover. Thank you.